So for problem number one, you're given the graph of a piecewise function and you're supposed to write a definition. So we'll start with f of x equals, and we know that there are two pieces, and so we're going to put two commas. And what I like to do is I like to define my domain restrictions first. So in other words, this first piece is defined between x equals 0 and x equals 3. So I'm going to go ahead and put 0 less than or equal to x, which is less than or equal to 3. So with functions, we have an input, which is the x, that's the input, and that's a member of the inputs are always members of the domain. And then we have the output. The output is the f of x. So in other words, if we put a 0 in, like f of 0, we can see from the graph that f of 0 is 1 because the point 0, 1 is on the graph of this function. Now if I plugged in 3, we can see there's a point 3 that has an ordered pair of 3, 4. So in other words, f of 3 then would be equal to 4. But if we were to plug in a number like 5, we wouldn't find it on the first piece, we would find it on the second piece because the second piece is defined between 3 and 5. So let's go ahead and set those up. And by the way, f of 5 would be equal to 3. So x has to be greater than 3 but less than or equal to 5 to use the second piece. So these right here, these are what we call our domain restrictions. They tell us which piece to use. If we're not going to even look at the graph, if we're going to look just at the piecewise function that's defined, which is what we're trying to do, write a definition, we're going to define f of x, and we then would not have to even look at the graph to find the y values, the outputs, depending upon whatever the inputs are. So that's kind of a overview of how piecewise functions work. Well, let's go ahead and define the first piece. The first piece you could see is linear, and this linear piece goes through the points 3, 4, and 0, 1. So actually we get a little bit of extra information about this function, this linear function. It has a y-intercept of 1. So we know that any line can be written in terms of slope-intercept form. And so if we can figure out the slope of this line, then we could put the slope and the y-intercept in this form, and we could have our definition for that piece of the piecewise function. So what's the slope? Slope is change in y, 4 minus 1, over change in x, 3 minus 0. 4 minus 1 is 3, 3 minus 0 is 3. So we know the slope of this piece is 1. In fact, if this line went all the way through in both directions, through the 2 points, it would have the same equation, y equals slope times x plus 1. So in other words, y equals x plus 1. But our piecewise function is only defined between 0 and 3 to be equal to x plus 1. Therefore, if we wanted to figure out whatever f of any number that is between 0 and 3, including 0 and 3, we could put in, let's say, 1.3. Well, that would be really hard to tell from looking at the graph. But if we know the definition for that piece, and we know that 1.3 is between 0 and 3, we would just have to take that 1.3 and add 1 to it to get 2.3. So defining the function is actually very helpful if we wanted to figure out the value of the function for other values of x that are not listed on the actual graph. So our more challenging part would be to figure out the equation for this piece here. Now we could see it's linear, and the first thing we want to do is we want to figure out what the slope would be if it did go through both of the points. We could see it goes through this point 5, 3, And if the line continued, then it would go through the point 3, 2. So we know then the slope of that piece of the piecewise function would be the difference in the y-coordinates, 3 minus 2, over the difference in the x-coordinates, 5 minus 3. And so we would get 1/2. So the slope of that piece is 1/2. That's an important piece of information, because if we want to find the equation of that piece, we could go ahead and plug in the slope and either point into the point slope form of a linear equation. Now, let me use a different color here. So let's just define 5 to be our x1 value and 3 to be our y1. So we're going to plug in 3 for our y1. We're going to plug in 5 for our x1, and we just found that the slope of the line that goes through those 2 points is 1/2. So we're just going to go ahead and plug that in. Y minus 3 equals 1/2 times x minus 5. So if we want to, we could just go ahead and add 3 to both sides to get y equals 3 plus 1/2 times x minus 5. And just to make it look nicer, we would want to go ahead and write this in slope-intercept form. We wouldn't actually have to do that, but since the other one is in slope-intercept form, I'm going to go ahead and do that, which is probably what most of you have done. So I'm going to take this equation, I'm going to write it up here where I have a little more room, and I'm going to go ahead and distribute the 1/2. So we get 3 plus 1/2 x minus 5/2. And all I have to do now is figure out what 3 minus 5/2 is. Well, 3 can be rewritten as 6 over 2. And 3 minus 5/2 would be 6 over 2 minus 5 over 2, which would be 1 over 2, 1/2. So we could rewrite this, the right side of this equation, as 1/2 x plus 1/2. And we're going to take that guy and put it right there, because that's the equation of the second piece. And again, I repeat, it is only defined, this function is only defined as 1/2 x plus 1/2 for the x values, or the inputs, between 3 and 5. Not including 3, but including 5. And that's it for that one.